Okay, we just did a quick exercise where I was holding this at an angle. Now let's pretend the angle was like this. Okay, just for demonstration. Let's actually pretend it's like this. Okay. Then I asked somebody to grab the other end and pull with about 3 pounds of force. So I'll do that all by myself. 3 pounds of force in this end, 3 pounds of force in this end. I got to be careful. I usually kind of tend to stretch out steel. Don't know my own strength. Actually, I do. So rubber bands maybe a little bit. Okay, so pull this. Okay, now I'm exerting a force on each end. And let's say it's about 3 pounds of force. We're on x-axis here and a y-axis here. Apparently the thing confused the camera because it just went completely out of focus. Back. Yes, right. Okay, so what I want you to do is sketch an arrow that represents the direction in which the force I exerted with this hand, as opposed to this hand. Well, what's the direction of the force I exerted with this hand? Okay. In degrees, more than 0, less than 90, right? Closer to 0, closer to 90. What do you estimate it will be? Just go ahead and sketch that vector on your paper. For the vector that you tell me what I'm going to do. Yeah. Okay. Okay. Lottie said 30 degrees, which kind of corresponds pretty well to my picture. I think that's a little more than 30, but less than 37. Okay. So it's pretty close to 30 or 30 degrees to be a perfectly okay angle. So I'm going to use 30 degrees. If you had a different estimate, a couple of you did, that's fine. Just depends on how you drew your vector. Okay. Okay, so if it's 3 pounds at 30 degrees, then we're going to model that with an arrow of length 3, representing 3 pounds. So now my question is, statement here, and we'll kind of prove this in lab later on. In a sense that we can make very real, this vector is the sum of 2 vectors. Okay, so I'm going to call this vector L. And I'm going to put an arrow over it, indicate there's a vector. It's an arrow that represents a physical quantity. That doesn't always have to be a physical quantity. You get abstract as heck. But for right now, physical quantity. Okay. And forces are probably the easiest ones to understand. Okay, so I exert a force in this direction. And I'm claiming, I'm actually stating, but we'll make sure we understand why. This force is equal to a force F sub x in the x direction. And of course, F sub y in the y direction. And we can find Fx and Fy by projecting this vector at a right angle onto the x-axis and at a right angle onto the y-axis. Meaning that we have a right triangle, the length of 3 here, and an angle of 30 degrees. Now, I'm not going to go over the definitions of sines, cosines, and tangents and stuff. I assume you know it, or can review it, or open math, and open your eyes to it. And they sign that we do the next class. Okay, so on vectors and a couple of other things. It's a pretty good introduction to vectors. Okay, I kind of like that sign. Incidentally, y'all did pretty well on the physics primer. If there were problems, the part on algebra tended to be a little lower on most, I'd say most papers, on most tests, and on calculus a little bit. Okay, because some of the later questions in calculus, got a little funny, but I don't see any cause for any concern there. I'll be able to deal with the calculus, the chain rule, and all that stuff. And we'll deal with that as we go up that. Okay. Because anyhow, on this triangle, we know that this side would have a length of 3 times the sine of 30 degrees. And this would be 3 times the cosine of 30 degrees. Okay, the sine being the opposite angle divided by the hypotenuse, the cosine being the adjacent angle divided by the hypotenuse. And I think everybody is at least familiar with that terminology, and it's really, you've been through it, you've had trigonometry, it's pretty easy. So it might be a little rusty. Well, then we're going to be able to say that the magnitude of Fx is 3 pounds, because of 3 is for pounds, right? 3 pounds times the cosine of 30 degrees. That's approximately, is what I'm getting isn't at all right. So I don't know what I was thinking, but it's about 2.6 pounds. Okay. I think that's what's the nearest tenth. It's probably 2.5 something. I think it'll round off. And your calculator will tell you that. You should know that the square root of 30 degrees is a square root of 3 over 2. And the square root of 3 is about 1.732. That gives you about 0.867 comes out. Okay. 1.732 divided by 2 is 8.8. I said 8.86. But I think it runs up to 0.87. Anyhow, and I'm not going to belabor that. Something in my mind is sitting right there. I think I'm off. Something like that. Okay, anyhow, Fy is 3 pounds times the sine of 30 degrees, which is equal to 1.5 pounds, because the sine of 30 degrees is 1/2. And you should also know why that is. Okay, very simple. If you put 2 30-degree right triangles next to each other like this is 30 degrees, This is 30 degrees and these lengths are equal, then this is 60 degrees and this is 60 degrees. Okay. And it follows that then whatever this side is, say this side has length L, well, I should say this side has length 1. This side has length 1/2. So immediately the sine is the opposite side over the adjacent, which is 1/2. And this side, by the Pythagorean theorem, is square root of 1 squared minus 1/2 quantity squared, which is a square root of 3 divided by 2. I need to work out the arithmetic. Everybody's totally competent to do that. You should always know this. And unfortunately, the emphasis on geometry and emphasis on calculators, not everybody does, even at this stage. And you should also understand how to do the 45 degree. Okay, those fundamental, 45 degree. This is equal to this. So if this is 1 and this is 1, this is square root of 2. So the sine is 1 over the square root of 2, cosine is 1 over the square root of 2. And we often write that square root of 2 over 2. Although the reasons for doing that are more historical. But it's a form thing. So, but I see a lot of physicists that go square root of 2. Used to be a good reason for that because calculations are cumbersome. It is easier to have the big decimal in the numerator than the denominator. Easier to divide into a long number than divide by a long number. So since nobody is multiplying or dividing big numbers anymore except calculator, the reason for the rationalized denominator system. Okay, that's just an aside. Now, do we understand this picture? Okay, that's basically what you do. Much of what you do with vectors. Okay, now I'll say that the other vector, the one exerted on this end, was equal and opposite to this one. How do I know it was equal and opposite? Well, because that bar wasn't going anywhere. Okay. And even if I'd have been walking with that bar, it would have still been equal and opposite. So the bar not going anywhere it isn't even necessary. The bar wasn't accelerating. As long as I was walking without accelerating, those forces would have been equal and opposite. Okay. So a basic principle, one of Newton's laws, and a little foreshadowing, is that if it ain't accelerating, there's no net force on it. Okay. Which means that these forces have to add up to 0. Meaning they have to be equal and opposite. Because if they aren't in opposite directions, they can't add up to 0. If they aren't equal and opposite, they won't add up to 0. So we have another force here. So now we've got like a force F1 with components F1x and F1y. And a force F2 with components X2x and so I write F2x, F2y. If the forces are in opposite directions, this angle is also 30 degrees or whatever you got. And whatever angle you got, you can calculate these easily with your calculator. You know you can find the sine, cosine. Okay, so we can now say that This angle is 32 degrees, so the magnitude of F2x equals, and F2 is also 3 times. I'm going to write it this way. F2 cosine theta, which is approximately 2.6 pounds. Magnitude of F2y is F2 sine theta, which is equal to 1.5 pounds. Okay. Now, when I write F2 without an arrow over it, that means the magnitude of F2. So I could put absolute value signs around the F2 and an arrow over it. F2 with an arrow over it and absolute value signs just means 3 pounds the magnitude of the force. Okay. And similarly with F2. Okay, well, so far, the vector F2x is clearly not equal to the vector F1x, isn't it? Because this vector is going this way, this vector is going this way, they're not equal. Now they are equal and opposite, because they have the same magnitude. Same number here, same number for the cosine of theta. Think about this one. How do we distinguish the two vectors? Just knowing the magnitude of their components. There are two ways to do it. The way the book likes to do it, and the way physicists usually like to do it. Is you just use a little common sense about what direction these things are in. So I'm going to introduce the I and J vectors so we can talk about what these components are, okay? So it's a unit vector in the positive x direction. By a unit vector, I mean a vector of magnitude 1. Then we have the J vector, which is a unit vector abbreviating this somewhat in the positive y direction. Okay. Now I can say, among other things, that F2x can be written as approximately 2.6 pounds times the I vector. Okay. If you multiply the I vector by 2, you get the I vector and another I vector. It's going to be a vector twice as long. If you multiply it by 3, well, it goes that much longer and it's this long. Okay. So, just to put it in context, here's I. Put I here and I here. I can see what the vector 2i is. Okay. Put 3 i's together. you get an even longer vector, which is 3i. And 2.6i is going to be between this and this, a little bit closer to this one. So maybe .6i might be. Okay, because this is longer than this. It's shorter than this. Okay. And I'm pretty sure I did get the 0.6 exactly right, but you get the idea. So there's just a picture. When you multiply a vector by a number, it doesn't change the direction of the vector. Well, actually, if it's a negative number, it reverses the direction. Okay. So we make a negative I. It's like this, negative 2.6i. Be just the opposite of 2.6i. Flip it around. Okay. That's pretty much all you need to know. Let's see if we can apply it. Okay, so okay, well, we expressed f2x as a multiple of a unit vector. How would I express f2y? Can you write that down on your paper? See if you're following this. Okay. So, question here. What's the difference between a vector with a magnitude around it and the vector itself? Okay. The vector itself has a direction. Notice the magnitude is just a number with units. And not even always with units, okay? So the magnitude is kind of just how big, how long it is. And this is how long this vector has to be if it's projected down from 10 positions. Okay? And this is how long this vector has to be if these are right angles. And what I'm saying is, I haven't said it yet, but the total force would be exactly the same if I had someone pulling in this direction with 2.6 pounds on the end of that bar, and somebody else pulling with 1.5 pounds this way. It would give me a force of 3 pounds in this direction. And if you were on the other end of the bar, you wouldn't be able to tell the difference. Now, I kind of want to digest, everyone wants to kind of digest that statement. And we'll make that really clear with something we'll do in lab. I'm going to blindfold you. We're going to have two people. You know, if two people are pulling this way and this way, or just one person pulling this way. Okay? Not really blindfold you. We don't want anybody stumbling over things. I'd ask you to look the other direction or close your eyes. You can't tell the difference. You just cannot tell. There's no difference in the effect of the force. And there are other ways to tell that. Okay, well, that's why we have the magnitudes of these things. And also, F2x is 2.6 pounds times a unit vector in the direction of F2x. Okay, so if we do 2.6 times I, it has same magnitude, especially that's 2.6 pounds. Okay. So then how would we do this vector? Well, it's going to be it's not in the direction of the I vector. Okay, the F2y is in the direction parallel to the J vector, but it's opposite. So we would express that as negative 1.5 pounds times the J vector. Make sure we've got a book on that J so we know which one it is. Okay, does that make sense? Okay, so now if everybody would take just a second and write down the components of F1x. And F1y. Okay, so F1x. Now F1x is in this direction. It's either in the direction of I or J or opposite the direction of one of these. Which one is it? Is this a multiple of I or multiple of J? Well, I is in the X direction. So it's going to be 2.6, negative 2.6 pounds times I. Negative because I is in this direction. And F1x is in this direction. Okay. And it's I because I moves the X direction. I is the vector in the X direction. When you multiply a vector by a number, you can't change the line of action of the vector, okay? The line along the direction of the line. Okay, you can change positive to negative. Okay, so it's any multiple of I is either going to be in the direction of I or the direction opposite I. Positive if it's in the direction of I, negative if it's the direction opposite I. Okay, so F1y is going to be plus, I'll emphasize the plus, although you don't really have to write it, 1.5 pounds times the J vector. Now that's not difficult to sort out if you need, you might need to think about it a little longer. It's not familiar to you. But there we have the F2x, F2y, F1x, and F11. Now, what I'm saying is that actually still on the screen here. This over a little. Okay. I'm going to take all this and put it together. And I'm going to say that vector F1 equals negative 2.6 I plus 1.5 J. And I'm going to write the units over here. I'm just going to put things around this and indicate it's in pounds. Sometimes you want to carry the units, sometimes it's totally understood what the units are, and you kind of suppress them, but you make sure you make a note that this vector is in these units. Now we can say that F2 equals, say carefully, 2.6 I minus 1.5 J. And it's in pounds. Now, what do you get? You add F1 plus F2. Well, I'm just going to write it out and then explain why it is what it is. Okay, so I'm going to suppress the pounds there, they kind of get in the way. Negative 2.6 I plus 1.5 J added to 2.6 I minus 1.5 J. I haven't proven it. Oh, we did in linear algebra, but I haven't proven it. But you can take the word of everybody who's in linear algebra. But when you add vectors, you have associative and commutative laws. And using associative and commutative laws, you can rearrange this as negative 2.6 I plus 2.6i plus 1.5j minus 1.5j and then you can factor out the coefficients of I. And we get 0i plus 0j. Okay. And 0i plus 0j is just plain old zero vector. We write that not as a number zero because it's a vector. Okay, we put an arrow over the top of it. Okay, so again, we see we had F1 and F2, we have commutative and associative laws, so we can just write out F1 and F2 suppressing the units. And then just rearrange these as though just plain old algebraic quantities. As we do have an algebra of vectors. And when we do that, we see that the negative 2.6i and plus 2.6i add up to 0, 1.5j negative 1.5j adds up to 0, meaning that F1 and F2 add up to 0, meaning that the net force, and let me just say this, the net force is zero vector. Now we'll see soon enough that this applies that the acceleration is zero. And you know from what we did last week, if the acceleration is zero, then the velocity and a derivative of zero, okay, unless it's a constant. Okay, we have a constant velocity. And the position then is and a derivative of constant. Okay, which is just a linear function. Now all that means is your graph is a straight line, graph of position versus time is a straight line. And you're moving at a constant velocity, constant speed in an unchanging direction. Okay. Now, that force is not always zero. We want to talk about, well, most assignments have a medically related question, and you'll appreciate that. Okay. Everybody should appreciate it because you're going to be under medical care, so you might as well learn stuff. Okay. And anybody become a biomedical engineer, who knows? But for sure what your path is going to be. Neat example there. Near and dear to my heart because I've had shoulder trouble. Try to reduce a separated shoulder. So you put first in a traction apparatus, and one arm of the traction apparatus pulls it this way, one arm pulls it this way. Okay, so you have a nice steady force, and there's no tendency for the shoulder to wiggle this way or this way. And that's the reason for the using two forces. And I think they give you two forces at 30 degree angles and ask you what the net force is. Okay, so that kind of motivates. Let's let that kind of motivate, because that's kind of easy to imagine. Let's let that motivate. Motivate me to wash outside of the board. Motivate vector addition. I have two vectors. Two ways to look at vector addition. I wrote it down here. Parallel with that. Two ways to look at vector addition graphically. One is you make a parallelogram out of this picture. So essentially, this vector is also F2. And this vector is F1. Now, one thing about vectors is you move them anywhere you want. They don't have to be rooted with yours. Okay. So we could make a copy of F1 and move it down here, copy of F2 and move it up here. And it's clear that we have a parallelogram because when you move a vector, it maintains its magnitude or length, but it doesn't change its angle, doesn't change its direction. So we can see that, yeah, to the extent that I drew this correctly, F2 is in the same direction here as it is here. Makes the same angle with the positive x-axis as this. And F1 makes the same angle with the axis as this one. Okay. And I drew F1 a little too long here. It needs it up to not quite at the right angle. Still have good pencil. So that here's F1 plus F2. Do that done by the parallelogram method. You could also do it. I'm just taking a copy of that one here. A copy of F2 here, put them head to tail. There's F1 plus F2. Okay. Now, either method works equally well for two vectors. If you've got three or more vectors, let's say you've got a different F1. And an F2. And an F3. How do you add these graphically? You do it head to tail. You might start with F1. It doesn't matter which one you start with, because again, addition of vectors is commutative and associative. So you can add them in any order, but obviously with the order they appear. Here's F1. Here's F2. And here's F3. It's all right if they cross each other. So that my result is F1 plus F2 plus F3. Neither picture would give us the same result. Here's F1, and we'll do F3. Then we'll do F2. Nothing, don't cross each other. There's no reason. Most times to avoid crossing each other, and some people think it's a little neater if they don't cross. So you kind of put them in order according to their angles, whatever. Okay. Stop. Have a session for writing out, please don't make any sense. If F1 is F1 cosine theta 1i, but F1 sine theta 1j. In other words, F1 has an angle theta 1 and a magnitude F1. So let's say here's F1 and here's theta 1. Here's F2. Here's theta 2. Now notice I've drawn theta 2 from the positive x-axis in the counterclockwise direction. If I do that, then I'm guaranteed that F1 can be expressed this way. Because this angle, being a third quadrant angle, gives you negative components. Or well, negative y component for F2. Because the sine of this angle, which is if this is 30 degrees here with the y-axis, this is 300 degrees. Sine of 300 degrees is negative. Cosine of 300 degrees is positive. In other words, if you measure your angles from the positive x-axis counterclockwise, you don't have to worry about pluses and minuses that happen automatically. Now, there are a few cases in physics where that's not a good idea. And that's not the way you're going to see it in the book, but I'm going to do it just for succinctness of notation here. Okay. And I'll often do it. We'll worry about cases where it causes trouble when they arise. So then if I want to add F1 and F2, as we saw before, I can just add the I components and add the J components. And yeah, I can certainly write F1 cosine theta 1i, F2 cosine theta 2i. I've got an I here and an I here. I can actually simply factor out the I. I can write this as F1 cosine theta 1 plus F2 cosine theta 2 quantity times the I vector. I can do the same thing. We ought to learn to think before I write. I do the same thing with the J components. I get F1 sine theta 1 and F2 sine theta 2, both multiplied by J. Well, there's my calculation scheme. Now, all we're doing is what we did here. We expressed F1 and F2. Well, actually, we did it over here. Okay, here's your F1 cosine theta 1i. Because your theta 1 in this case was 180 degrees. Okay. The angle of F1, if you measure from the positive x-axis, is 180 degrees, and the cosine of 180 degrees is -1. So you get -2. Well, that's, sorry, that's the angle of F1x. The angle of F1 is, if this is 30 degrees, this is 150 degrees. You punch in the cosine of 150 degrees, you're going to get negative 0.86, basically. 0.87. Negative square root of 3/2. Your calculator is going to give you a number. And when you multiply it out, you're going to get to negative 2.6. Same as we did here. Now we can see, yeah, we see this vector is a little shorter than this one because this is a right triangle, and this is hypotenuse. So the adjacent side here is clearly shorter than the hypotenuse, not that much. Okay. So if this is length 3, the fact that this is length about 2.6 makes perfectly good sense. Okay. Anyhow, again, take at 150 degrees, multiply the cosine 150 degrees by the magnitude 3, we get this. And the sine of 150 degrees is still positive 1/2. We get this. And then with the angles for F2, F2 would be what? It would be 300 degrees minus 30, would be 330 degrees. Sine is negative 1/2, 330 degrees. Cosine is positive, approximately 0.87. Okay. So we've already illustrated what I've written in symbols. Here, this is not necessarily a formula you want to memorize. It's just a process we've already illustrated. And I'm just using these things to put it in, using these, cosine theta 1, sine theta 1, etc., F1, F2, to symbolize the whole process. Okay, it's just what you naturally do after you've done a few problems. It's clear if I had 3 forces, how would the result differ? Or how would the process differ? Well, if I have 3 forces, I've got an F3 with an angle theta 3, so I'm going to have F3 cosine theta 3 my I, and an F3 sine theta 3 on my J. If I've got a whole column of vectors, probably want to go to an Excel spreadsheet, line everything up, and then just add columns. Because this lends itself to just being written as a table. And so if you see that, I'm giving you the idea of what you're going to see in a little more detail and formulated in a coherent way. And I think I've used OpenMath, but in your MyLab. Okay. Okay, so all that is actually pretty straightforward. It also applies to velocity vectors, okay, or acceleration vectors. If I'm moving in that direction, this is my X direction and this is my Y direction, then I've got a component of my motion in the X direction and a component in the Y direction. So these things could be velocity vectors. Now, if I'm moving that way in this room, and this room is moving that way, I'd add those 2 vectors to get my velocity with respect to whatever frame of reference the motion of the room was measured in. I'll talk more about frames of reference, but I'm just giving an example how velocities would have. Accelerations would have the same way. So if this room is accelerating, I'm accelerating in this direction, room's accelerating in that direction. That's my net acceleration relative to the surface of the earth at this, in the vicinity of this point. Or if I toss a ball out of a car with a certain velocity, okay, certain direction and angle, then the car is moving in some other direction. That ball's going to come up with the resultant velocity angle. And I just have those as vectors. Okay. So just a couple of examples. And lots of other things. Now there's another one I want to talk about, but maybe not. So to talk about it. Maybe we'll save it though. Okay. So it motivates the cross product. To motivate the cross product, we look at the motion of that beam. Rotational motion of that beam. It turns out the only way that we can explain that with vectors, the only way we can explain everything that happens with vectors is if a beam rotating this way has an angular velocity that's a vector in this direction. And nothing's moving in this direction. Okay. So if I ask you what arrow represents motion around this way, you want to give me a curved arrow, but vectors don't curve. You've got this thing called the right-hand rule that tells you it's moving in this direction and the vector's this way. So you want to kind of just, I want to get your brain cells just started on that idea. We'll make more of it next time. And your angular acceleration is in that direction or that direction, depending whether it's speeding up or slowing down. And that way, have you ever seen what happens? You take a bicycle and get it wheel and start it spinning and try to move, change its direction. You ever done that? Yeah, we'll do that. I think I remember where the bicycle was. Okay. Back to more mundane things. Now let's say I've got a vector here. A vector here. About these vectors v1 and v2. v1, if you like, v1 stands for velocity, but it you generally use it to represent vector 2, so it could represent any vector. Let's just go ahead and estimate on this. Let's say that V1 is (5.1i plus 2.8j). I don't want it to be that with 2.3j. Okay, V2 is okay. Now I'm going to do a calculation called the dot product. I'm going to show you what dot product is. First, your linear algebra. Let's refresh you a little bit. The dot product V1 dot V2 is very easy to calculate. Okay. You just multiply the I components, multiply the J components, and add them. I picked that. I'm wishing I had made the angle a little bigger there. But Okay, that's about 36, but you gotta take off about 5%. 8%. 8%, 36, I'm gonna say it's about 33. Ballpark. And that would be 14.6 down. This comes out anywhere near right, I'd be surprised. I'm doing calculations in my head. About something. Okay, so it's an easy calculation, right? Multiply the I components, multiply the J components, you got the dot product. All right. Now the magnitude of V1 is square root of 5.7 squared plus 2.3 squared. Okay, I think 5.7 squared is 2, and that's 2.3 squared. So that's about square root of 37. Very approximate 6.1. And the magnitude of V2 is the square root of 5.9 squared plus 7.2 squared. Pretty close to 36. That's a little more than 49. So I'm going to say 36 and 51. Square root of 77. And that's approximately 7.7 or 7.8. Overestimated, just so I get a decent result. Okay. Okay, now here's the neat thing. This incidentally can be proven using high school trigonometry, using the cosine, the law of cosines. Okay. So you can prove that this is true. We're not going to bother with the proof. We're just going to use it. Goes against my mathematician nature, but it's okay. I have a little bit of mercy. Okay, so V1 dot V2 is equal to the magnitude of V1 magnitude of V1, V2 times the cosine of theta, where theta is this angle. So what's neat is, if I know these vectors and know the law of cosines, I can figure out what this angle is. That's pretty cool. Especially when you realize that if we have motion in 3 dimensions, and we're not going to talk about that anytime real soon. But if something's moving in 3 directions, you just add a k vector in that 3rd direction, perpendicular to the I and j vectors. You have I, j, and k. And now you've got 3 components, I, j, and a k component. Dot product is the same thing. You just multiply the k components and add them in. Okay. Then the Pythagorean theorem works in 3 dimensions, just as well as it does in 2. Generalizes. So in 3 dimensions, it's really easy to do the same thing. And when you talk about 2 vectors in 3 dimensions, it's really hard to visualize what the angle is, even if you've got a picture. Okay. You'd have to view them from a perspective perpendicular to the plane they live in. And the plane is not the x1 or x2. You know, okay, it gets complicated. Not only that, but you can talk about the angle between 2 vectors in 48 dimensions if you want to, because the dot product works fine in 48 dimensions. So does Pythagorean theorem, in general. Okay, so the really neat thing is that this gives you information that goes up to any number of dimensions, even the past 3 dimensions we can't even visualize. Okay, well, so here's V1 dot V2. How am I going to calculate theta? Well, I want to calculate theta. If I can find the cosine of theta, then I can find theta using the inverse cosine, right? You got a button in your calculator to do that. So cosine of theta is this. Okay, well, if you believe my calculations, this is 47.8. That 0.8 is kind of ridiculous. 48 would be better, more appropriate to the accuracy of my calculations. But that's over 6.1 times 7.8. At this point, I want you to take your calculator and figure out what that angle is. But before you do, just so you can hold me accountable, I want you to estimate how many degrees you think that is. Okay, so we've got estimates generally a little under 30 degrees, 20-some degrees. So as low as 20, as high as 27 or something like that. When you do this calculation and take the inverse cosine, inverse cosine of all this goes into the inverse cosine. So that's going to be approximately 27 or 28 degrees, usually 27 point something. Everybody got close to that. Again, that's why your calculators gave you different numbers. I might have read one of these numbers a little bit first. But everybody did the right thing and did it almost immediately. So that's good. So now you know how to find the angle between 2 vectors. Now, what would you do if I gave you the angle and magnitude of V1 and the angle and magnitude of V2? Well, you would do this. You'd use the cosine and the sine to find the components and use the components then to calculate the dot product. Well, if I gave you the 2 angles, you would know what the angle between them is. So you could find the dot product if you wanted to. Anyhow, you're going to see a lot of this in your assignment, but you should be well equipped to do it. Now, there's other stuff in your assignment about units and stuff like that that everybody did quite well on in the physics primer. So unless I see an issue come up, I'm not going to talk about those things. Okay, I'm going to concentrate on the things that you might find to be a challenge. Then next time we'll build on this stuff with vectors so that we can talk about vectors for rotation. You won't need that for your assignment, but it gives you a better understanding of why you do cross products. Because the next assignment does cross products. They're not hard to calculate. They're a little bit different because the cross product is perpendicular to both of the vectors that you're crossing. Calculation scheme is easy enough. Okay. Very good. I think y'all are doing quite well. Okay. A few little glitches. On some of the topics, but nothing's going to cause us problems in the short term. By short term, I mean like for the rest of the month.